Okay, so I thought I'd try a few electrophilic aromatic substitution reaction problems. Here are some problems from your textbook, chapter 5, that I grabbed. We can try problem A to begin with. Number 33A. So we have chlorobenzene, and this is, if you recall, Friedel-Crafts alkylation. So we're going to put the ethyl group on. It's going to be attached to the ring where the chlorine is. The chlorine on the ethyl group, that is, not on the ring. The question is, will this go ortho-para or meta? Should I put the ethyl group in the meta position or in the ortho and para positions? Well, what should you look at? Should you look at the ethyl group that you're putting on, or should you look at the chlorine that's already on the ring? You look at what's already on the ring. And this is an OP director. So we should get our ethyl group there. That's ortho plus para. I'll just draw the ortho, but we could also have the para, which, well, I guess I'll draw it. Okay. Now, some of you might remember that it says Friedel-Crafts alkylations have some limitations, and one of those limitations is that it does not work when you have a group that strongly withdraws electron density from the ring. So this was a slide that I had in that discussion about these limitations, and the key word here is strongly electron withdrawing. And if you look, halogens are not in the list. Halogens are, if you recall, weakly electron withdrawing overall. They're kind of in between the activators that are all ortho-para directors and the meta directors that are all deactivators. They're sort of in the middle on that chart. So they're deactivating, yet they're ortho-para directing. So they're not very strongly electron withdrawing. So this reaction will work even though those are deactivators. Let's try B. Now for B, you might say, oh, how am I going to do this? There's two rings. Well, we're going to assume we're just adding once. And what are we adding? It's another Friedel-Crafts. But it's an acylation now. If you recall, this is something with the electrons on the atom bonded to the ring. That's an OP director. And this is actually an activator as well. So let's work with the ring on the left. Where will this group go? Will it go ortho or para? So let me draw para. So I put a para. That's para plus ortho 2. So I could put an ortho to the oxygen. Ortho would be right here or to the other side. There's two ortho positions. What about D? we doing with D? Here we have two ethyl groups on the nitrogen. You see that lone pair on the atom bonded to the ring. That's going to be an activator orthopara director. And what are we trying to put on the ring here? This is sulfonation. Sulfonation. So nitrogen is an OP director. So we can put this ortho. And I could draw a para also. Okay. Now problem C is nitration. So here's another problem that goes with nitration. There's a lot of them. I'll pick a couple here. It says we're going to do a mononitration. That means we react with HNO3 and H2SO4, and we add NO2 to the ring. Okay, so let's take a look at A. That is bromobenzene. And this is an orthopara director. Despite being a deactivator, it is an orthopara director because of the lone pairs on that atom. So we're going to do nitration. And this will go para. We'll also get ortho 2. And the question, 35, the question is, which of these will react faster and which will react slower? Well, this is a deactivator. So the reaction is slower than with C6H6 benzene. Okay, so if we try benzoic acid, we see that benzoic acid is a deactivator and a meta director. And the reason why is because you have this slightly positive carbon that positive carbon bonded to the ring removes electron density and deactivates the ring. So if we nitrate this, and all deactivators are meta directors except for halogens. So this is going to go meta. And this will be slower than reaction with C6H6. And then finally, let's try phenol. This is an activator. It's pretty far to the right on this scale. It's quite a strong activator. And sometimes for some of these reactions, like if you try to halogenate, put a chlorine on, for instance, you might not even need the Lewis acid catalyst to make it work because it's such a strong activator. And all activators are OP directors. So we could get our nitro group para and ortho 2. Okay, so those are some examples for you to try. Maybe work out the other ones, see what you get.